The molar mass in grams per mole of each element can be found in the periodic table. We will also be interested in knowing the molar mass of compounds or combinations of the atoms that exist in the periodic table. Let's see how we can figure that out. Let's start by looking at the two covalent compounds depicted here that are made from carbon and hydrogens. The first compound can be symbolized as CH4, and the second compound can be symbolized as C2H4. The main concept here is that if I have a mole of these molecules, so I just replicate this 6 times 10 to the 23rd times, I will have 6 times 10 to the 23rd carbons, because each one of those has one carbon atom, and I will have 4 times 6 times 10 to the 23rd hydrogens, because each one has 4 hydrogens. So I will have 1 mole of carbon and 4 moles of hydrogen if I have a mole of these molecules. The analogy is that this table is made up of 1 tabletop and 4 table legs, just like this molecule is made up of 1 carbon and 4 hydrogens. So if I have a dozen of these tables, I will have 1 dozen tabletops, and I will have 4 dozen table legs. And those things together make 1 dozen tables. We can apply that concept to the CH4 molecule and find the molar mass of CH4 by adding up the molar mass of 1 carbon and 4 hydrogens. There's 1 carbon in CH4, and there are 4 hydrogens, and so we need the molar mass of 1 carbon and the molar mass of 4 moles of hydrogen. From the periodic table, the molar mass of carbon is 12.011 grams per mole. We have 1 of those, plus 4 times the molar mass of hydrogen, which is 1.008 grams per mole. If we add those together, we get 16.04 grams per mole of CH4. Now it's your turn to calculate the molar mass of C2H4. You should end up with 28.05 grams per mole of C2H4. Ionic compounds don't exist as discrete units. Rather, they are extended lattices of alternating cations and anions. Therefore, it may not be as obvious how I would want to add up the masses in order to get a molar mass for something like sodium chloride or potassium sulfide, both of which are ionic compounds. Remember that the way we symbolize these compounds is by using the lowest whole number ratio in the lattice for that ionic compound. So there's 1 sodium and 1 chlorine as a unit that makes up this repeating extended lattice. So when I'm calculating the molar mass of an ionic compound, I use these lowest whole number ratios to calculate the formula mass, or the mass of 1 formula unit. A formula unit consists of the number of cations and the number of anions as shown in the symbol for that compound. So a formula unit for sodium chloride would consist of 1 sodium and 1 chlorine. A formula unit for potassium sulfide would consist of 2 potassiums and 1 sulfur. This works because no matter how much of this sodium chloride compound I take, I will always have 1 sodium and 1 to 1 chlorine. So if I take a whole mole of this, I'll have a mole of sodium and a mole of chlorine. If I take a mole of potassium sulfide, I'll have 2 moles of potassium and 1 mole of sulfide. Thus, calculating the molar mass for an ionic compound is no different than calculating the molar mass for a covalent compound. I simply add up the masses of each of the atoms in my formula for the compound. So, for the instance, for sodium chloride, I would have the mass of one sodium atom, which is 22.99 grams per mole, plus the mass of 1 mole of chlorine, which is 35.45 grams per mole. So that's for the sodium, that's for the chlorine, and when I add those together, I get the mass of sodium chloride. So 22.99 plus 35.45 is equal to 58.44 grams per mole of sodium chloride. Now it's your turn to calculate the molar mass of potassium sulfide. You should end up with 110.3 grams per mole.